In this video, we talk about a well-known condition that, along with the Cauchy Riemann equations, will be sufficient to guarantee the existence of the derivative of a complex valued function. The Cauchy Riemann equations, while a necessary condition for the existence of the derivative of a function, will by itself not suffice to guarantee the existence of the derivative. And so, we need at least one additional condition to ensure the existence of the derivative. In this video, we will talk about a well-known sufficiency condition and its proof. Let z be equal to x plus I times y, where x and y are real numbers. Let f of z be equal to u of xy plus I times v of xy, where u and v are real valued functions. Suppose that f satisfies the Cauchy Riemann equations, where u sub x equals v sub y and u sub y equals minus v sub x. U sub x, v sub y, u sub y, and v sub x are the partial derivatives of u and v with respect to x and y. Suppose that in addition to satisfying the Cauchy Riemann equations, the partial derivatives of u and v are all continuous at z. Then f prime of z exists. We start the proof with the difference quotient f of z plus delta z minus f of z all over delta z. Let delta z be equal to delta x plus I times delta y, so that z plus delta z corresponds to the point x plus delta x, y plus delta y. Without loss of generality, we take delta x and delta y to be both positive real numbers. The difference quotient looks like this, with the coordinates of z plus delta z and z. In terms of u and v, this is the difference quotient. We split up the difference quotient into its real and imaginary parts. We will not go straight from z or the point x, y to z plus delta z or to the point x plus delta x, y plus delta y. We will make a detour by first going vertically from the point xy to the point x, y plus delta y. So we subtract u of xy from u of xy plus delta y, and similarly, we subtract this time v of xy from v of xy plus delta y. Then from the point xy plus delta y, we proceed horizontally to the point x plus delta x, y plus delta y. Algebraically, this corresponds to subtracting u of xy plus delta y from u of x plus delta x, y plus delta y, and v of xy plus delta y from v of x plus delta x, y plus delta y. This way, we change the form of the difference quotient while preserving its value. Let's examine the real part of the difference quotient. We split up the numerator into two differences. Each difference is over delta z. The terms in the first difference have the second coordinate fixed at y plus delta y, but the first coordinate varies from x to x plus delta x. So we define a function g that depends on the first coordinate and rewrite the difference between these two terms as g of x plus delta x minus g of x. Now it's time for the mean value theorem. The mean value theorem says that there should exist a real number xc between x and x plus delta x, such that g of x plus delta x minus g of x equals g prime of xc times the quantity x plus delta x minus x. The real number xc corresponds to the point xc y plus delta y between the points x y plus delta y and x plus delta x y plus delta y. G prime is actually u sub x, so that g prime of c is u sub x of c y plus delta y. X cancels out, so that the first difference is u sub x of c, y plus delta y times delta x. Similarly, the second coordinate in the second difference is the one that varies, while the first coordinate is fixed at x. And so we introduce another function h that depends on, this time, the second coordinate, so that this difference equals h of y plus delta y minus h of y. The mean value theorem says that there should exist a real number c between y and y plus delta y, so that h of y plus delta y minus h of y equals h prime of c times the quantity y plus delta y minus y. The real number psi corresponds to the point x psi between the points xy and xy plus delta y. H prime of psi equals u sub y of x psi. Y cancels out so that the second difference is equal to u sub y of x psi times delta y. And we shouldn't forget that everything is over delta z. We manipulate the terms in this last expression and rewrite the expression in the following way. From u sub x of c y plus delta y, we subtract u sub x xy. We also have to add back u sub x of xy so that we retain the value of u sub x c y plus delta y. Similarly, from u sub y x c, we subtract u sub y x y and add back u sub y x y. We'll call this difference epsilon sub 1. We'll call this difference epsilon sub 2. We separate the non-epsilon terms from the epsilon terms. Now u sub x of c y plus delta y tends to u sub x of xy, and u sub y of x c tends to u sub y of xy as delta z tends to 0. This is because the points c y plus delta y and x c both tend to the point xy as delta z tends to 0, and also because of the continuity of the partial derivatives of u and v. Therefore, u sub x of c y plus delta y minus u sub x of xy tends to 0, as does u sub y of x c minus u sub y of xy as delta z tends to 0. Therefore, epsilon sub 1 tends to 0, as does epsilon sub 2 by their definitions. Now, the absolute value of the real part of a complex number is less than or equal to the absolute value of the complex number, so that the absolute value of delta x over delta z is less than or equal to 1. The same thing is true for the absolute value of the imaginary part, so that the absolute value of delta y over delta z is less than or equal to 1. Therefore, delta x over delta z and delta y over delta z are both finite complex numbers. Therefore, since epsilon sub 1 and epsilon sub 2 both tend to 0 as delta z tends to 0, epsilon sub 1 times delta x over delta z tends to 0, as does epsilon sub 2 times delta y over delta z. We carry out a similar set of manipulations for the part involving v. We transform the part involving v in a similar fashion. C sub 1, like C previously, is between x and x plus delta x. And just like C, C sub 1 is between y and y plus delta y. As with the fraction with the u terms, the calculations proceed with the v terms almost exactly in the same way. Epsilon sub 3 and epsilon sub 4 are defined similarly to epsilon sub 1 and epsilon sub 2. Like the epsilon sub 1 and epsilon sub 2 terms, epsilon sub 3 times delta x over delta z tends to 0, as does epsilon sub 4 times delta y over delta z, as delta z tends to 0. Since the epsilon terms all vanish as delta z tends to 0, the difference quotient has the same limit as the sum of this quantity and this quantity. And finally, we get to use the Cauchy Riemann equations. U sub y equals minus v sub x, and v sub y equals u sub x. We factor out 1 over delta z and u sub x from the u terms. Don't forget the I that is attached to u sub x times delta y over delta z. And so this is what comes out of the u terms. We factor out v sub x from the v terms. We factor out I, and keep in mind that -1 equals I times I, so that after factoring out 1 over delta z, we rewrite the part with the v terms this way. Delta z is equal to delta x plus I times delta y, so that delta z cancels out. Therefore, the difference quotient tends to the limit u sub x plus I times v sub x. Therefore, f prime of z exists and is equal to u sub x plus I times v sub x, or applying the Cauchy Riemann equations, v sub y minus I times u sub y.